Hello everyone, this is Jianhe from Virginia Tech. So today is the last of 6 webinars sponsored by MAUSI and VDOT. Today we're going to have the 2 presentations. The first presentation is on developing a real-time energy and environmental monitoring system, and the second one is on investigating attractiveness of tolling roads. You have 3 options for audio connection. So the first one is using VoIP, which is your computer speakers. The second one is having the audio system call you. In that case, you need to type in your phone number at the prompt as shown on the right. This option calls dial out. And the third option is dial into the conference, which is also shown here. But in this case, if you choose this option, you need to first call using the phone number which is provided, and also after that you need to enter a PIN code which is also provided. So to increase the interactivity, you have 3 options. The first one is you can write questions and comments in the chat box on the left side of your screen. Also, after each presentation, we'll try to address any questions if you have from the speakers. You can also type in your questions and comments on the chat box on the left. And also, there will be several polls, and some speakers may ask you to respond using the chat box. MAUSI stands for Mid-Atlantic University Transportation Center. It's a consortium of 6 universities led by Penn State University, along with University of Virginia, Virginia Tech, Morgan State University, West Virginia University, and University of Maryland. It's a tech transfer project, which is a joint effort by University of Virginia and Virginia Tech, with additional support from VDOT, and the goal is to disseminate webinars of MAUSI projects at the 2 universities. And it is held second Thursday in the month at 2 p.m., but as I mentioned, today is the last webinar. We can issue a certificate for your attendance. It's for 1.5 hour contact hour for attending today's webinar. If you would like to receive one certificate, please email your request to Dr. Ihab El-Shawarbi at shawarbi@vt.edu, and please send your emails by Monday, December 15th. So I'll let you take a note if you would like. So again, the email address you're going to need to send your request is shawarbi@vt.edu. You can also see the presentations from University of Virginia's website. If you go to the Center for Transportation Studies through the University of Virginia's website, you should be able to see the MAUSI. You're going to see several tabs. You can find the MAUSI tab, and from there you can find today's webinar presentations and also the previous presentations as well. Here is the first poll. So the question is, who are you? You're going to see multiple choices: consultants, state government, university, faculty.
To answer that.
All right, moving on to the next poll. So the question is, how many people are viewing with you?
No, just yourself. One.
All right, so moving on to the third poll, which asks you about your familiarity with the first topic, which is real-time energy and environmental monitoring systems. How familiar are you with this topic? All right, so moving on to the last poll. So for the second topic, how familiar are you with the tolling road strategies? Right, moving on. So as I mentioned, we're going to have two topics today. The first one is developing a real-time energy and environmental monitoring system. And the speaker is Dr. Kyoungho from Virginia Tech. Then we're going to have a discussion after that. And the second topic is investigating attractiveness of tolling roads, presented by Dr. Jianhe from Virginia Tech. And we're going to have the second discussion after the second topic. And please, after the second discussion, please take a few minutes to answer a very short survey at the end of the webinar. We really appreciate that. So I'll let the first speaker start his presentation. Dr. Kyoungho is from Northern Virginia.
Okay, thank you. Thanks for joining the presentation. I know some of you are preparing your final exam and last minute of this semester. So I try to make this presentation very simple, and I hope you learn something from this presentation. My name is Kyoungho, and title of this presentation is Developing a Real-Time Energy and Environmental Monitoring System. And this study is prepared by myself, Kyoungho, and Dr. Sang-Jun Park and Dr. Shamlaka. The goal of this project is developing a real-time energy and environmental monitoring system using real-time traffic data. The developing model can be used as an application for dynamic low emissions zones. In this study, the real-time traffic data can be connected vehicle data, and I will explain dynamic low emission zones later in this presentation. This project is still in progress, so I will focus on the development of fuel consumption and emission model for this project. Background of the project. Surface transportation has significant impact on the environment. Transportation sector in the U.S. accounts for 30% of greenhouse gas emissions and 70% of U.S. fuel consumption. And also, surface vehicles represent almost 84% of the transportation sector greenhouse gas emissions in the U.S. And a key program of MAP21 is environmental sustainability to improve the performance of the transportation system while protecting and enhancing the environment. And here is my first poll. Have you ever heard about the connected vehicle technologies and research programs? Okay, it seems many of you are familiar about the connected vehicle research. And my second poll is, have you ever heard about the ALICE program? Okay, it seems most of you have heard about that, the ALICE program. I wanted to check how many of you are interested in environmental applications in connected vehicle research. All right, there's something called ALICE program, and which is the applications for the environment real-time information synthesis program. It started by the US DOT a few years ago, and the ALICE is one of the connected vehicle programs which utilize vehicle-to-vehicle and vehicle-to-infrastructure communications to improve fuel efficiency and air quality, and of course mobility and safety as well. There are several programs within the ALICE programs, which include eco-signal operations, dynamic eco-lanes, dynamic low emissions zones, eco-travel information, and support for alternative fuel vehicle, and eco-ICN. And our focus program is dynamic low emissions zones. This program geographically defines areas to incentive green transportation choices or restrict specific high-emitting vehicles to improve the air quality within a low-emission area. Using our proposal study, we can contribute the program by monitoring real-time energy and emission levels and by detecting high polluting areas. And here is another poll. Have you ever heard about any vehicle energy or fuel consumption and emission models? Okay, one of the key components of the project is to develop a proper energy and emission model that can be used for this project, specific project. So the energy and environmental model is typically derived from a relationship between fuel consumption or emission rate and the measurement of various variables, including vehicle power, force, or vehicle speed and acceleration, or other factors. another poll. Do you know the difference between macroscopic and microscopic energy and emission models? Okay, I wanted to check this question because there are big differences between macroscopic model and microscopic models, and many of you know about the differences. Okay, for example, if you drive like a constant 15 miles per hour for 1 hour, or if you drive your car between 10 and 70 miles per hour for 1 hour because of traffic congestion, and ended up your average speed is 50 miles per hour. In case of microscopic models, it gives you exactly the same result for 2 cases, but for microscopic model, the constant 50 miles per hour driving will give you much lower fuel consumption and emission rate, typically. So if you usually want to identify the impacts of traffic congestion or traffic signal operations, then microscopic models typically produce more reliable results. Major differences of macroscopic and microscopic fuel consumption emission models are input variables and output variables. And EPA's mobile and MOVES models are typically macroscopic models, and the MOVES project model and BT Micro, BT CPFM, and CMA models are considered as microscopic model. And macroscopic models typically use average vehicle speed to represent the vehicle's activities, but microscopic models use more detailed input variables, such as instantaneous vehicle speed and acceleration or vehicle power. For this project, we use the database of MOVES model because the MOVES database includes most up-to-date energy and emission data. It was developed by US EPA and is still updating. And MOVES can be used for transportation conformity in air quality non-attainment areas, which is required by federal regulations. Also, MOVES has integrated the most up-to-date data, and it was recently updated with 2014 database. And users can use for both macroscopic and microscopic modeling, and it can generate PM, particulate matters, and greenhouse gas emissions as well. And MOVES has GUI, so it's more user-friendly than other text-based programs. MOVES can estimate HCCO, NOx, NH3, SO2, PM10 and PM2.5, and greenhouse gas emissions, and toxic emissions, and energy rate. Here's a vehicle type that we can use for the MOVES, and it includes passenger car, passenger truck, a motorcycle, light commercial truck, intercity, transit, and school buses, and other types of trucks. And this is the screenshot of a MOVES model when a user first starts the program. And here's the screenshot of a MOVES model, which is ready to run. Can you see the all check marks over there? You have to provide all the inputs, otherwise the program doesn't work. So, for example, as you see in this scale section, you have to select either national or county or project level. And also there's a section for computation type. Based on the scale, input formats are different. So users have to complete all the inputs. moves emission rates. Moves include different emission rates for each combination of input variables. It can be fuel type, like a gas or diesel, and also light-duty vehicle or light-duty truck, like a vehicle type, and vehicle model year, 2001 or 2005, and vehicle age groups, and operating mode. And for operating mode, you need to, it depends on the vehicle speed and acceleration. So there's something called the VSP, vehicle specific power, and I'll explain this later, this presentation. To run moves, users should prepare a run specification. It's also called the run spec, and input database. Moves is a database program, so it requires an input database. Then moves can generate out database. Database can be viewed and manipulated in MySQL, and information can be exported to another program like Microsoft Excel. Moves has 3 scales, which are national level, county level, and project level, as I mentioned. And project level analysis can identify the energy and environmental impacts of specific transportation projects, such as highways, intersections, interchanges, and transit projects. Also, it is required for quantitative hotspot studies for conformity. Users should enter project-specific database using PDM, which is the project data manager. And Moves has 3 vehicle speed input options, which are average speed, OP mode distribution, and driving cycle. As you see from the screenshot, PDM requires many input database. Users have to complete individual tasks. And the database include fuel, IM data, vehicle age distribution, sync data, and OP mode distribution, and driving cycle, which is second by second vehicle speed and the roadway grade, and other database. In fact, completing this project data manager is one of the most difficult process to run both. And also, some of the data are not easy to obtain. So there's some difficulties to use Moves model for our project. First, as I mentioned, it is very complicated to prepare all input database. Second reason is computational time. Moves are a very heavy program. Typically it takes a few minutes, or sometimes it's more than 10 minutes to obtain a result. For the same computation, MATLAB can do it less than a few seconds. And the last most important reason is Moves generate only aggregated result of entire scenario. For example, let's assume you want to figure out the CO2 emission from certain section on Interstate 66. And if you want to identify the concentrate of CO2 emission at every milepost, it will be really difficult to figure it out from Moves, because Moves only produce total emission for entire section. So in this study, we used the core computational module and the database of Moves. And we'll develop the interface of Moves so that you can use it for the proposed real-time energy and environmental monitoring system. Main core computation part of Moves is finding this operational mode. It is decided by ranges of vehicle speed and vehicle specific power. The table shows operational mode being definitions for energy consumption. For example, if a vehicle speed is 54 miles per hour and DSP is 7, then you can find OP mode is 35 here from this table. DSP is vehicle specific power, and this equation show you how to calculate DSP, and it requires instantaneous vehicle speed and acceleration and load rate grade. In DSP coefficient for 13 vehicle types are available in the source use type table in MOVE's database. So the different vehicle types have different DSP coefficients. Okay, here's the fun part. Let me show you how to find energy rate from the MOVE's database. First, you have to find emission rate table from MOVE's database. The database includes source bin ID, POL process ID, and OP mode ID, and mean base rate. Source bin ID is 19-digit numeric data, and the one is just the first one is input value, and the FF represents the fuel type. Either it can be gasoline or diesel, and next TT represents engine type, such as internal combustion engine or electric engine. EE represents vehicle types, like a passenger car or truck or bus, and YY represents vehicle model year, such as 2014 or 2010, and SSSS represents engine size, and the last WWWW typically is all zeros. And POL process ID defines pollutant ID, such as HCCO or energy rate. And for OP mode ID, it is operational mode. We just saw it from the table. And mean base rate is base emission consumption or emission rate. Okay, here is the example how to find energy rate using MOVE's database. If you want to estimate fuel consumption of model year 2014 light-duty vehicle using gasoline with IC engine, and when vehicle is operated at 85 kilometers per hour with zero acceleration, then based on the DSP equation, DSP value is 7.6. And based on the OP mode table, OP mode is 35. And based on the lookup table from the MOVE's database, the zero rate in this case is 33.44 miles per gallon, which is reasonable for relatively low speed highway driving. But if there is some acceleration behaviors, then it will increase DSP and eventually generate a higher fuel consumption rate. And for this example, I use default values for other factors such as fuel, temperature, and IM, and air conditioner impacts. Okay, I compared this new approach with other microscopic models such as DT micro and CMM models, and I used EPA highway fuel economy test cycle and used 1995 passenger car with gasoline engine. And this figure shows the speed profile of the driving cycle. The maximum speed is around 100 kilometers per hour. And you can see some speed variation during the trip. And here is the operational mode distribution of the trip. And you see about 39% of trip is been zero, which represents braking and deceleration behaviors. And here are the results. As you see, all three models generate very similar results. And the new method using MOVE's database generates 0.94 liters, and BT micro generates 1.07 liters, and CMM model produce 0.989 liters. And also the figure shows that the patterns of second by second fuel consumption rates are very similar. Okay, as I mentioned, this project is still in progress. And so next step is the development of the MATLAB interface using 2014 MOVE's database. And also we'll test the model with connected vehicle field data, such as OBE and RSA field data. Okay, this is it. Any question from this presentation?
Thank you, Dr. Kyoungho. I guess we have one question I can see in the chat box. What format does the data have to be in?
Okay, this MOVE's interface will use just like a second by second speed and acceleration. But we can also input from the, we can use input from the average speed as well, because there's a typical driving cycle from the EPA's multiple driving cycles, so you can just pick it. And in case of other inputs like a temperature or the air condition impact, something like that, we just use the default values. So you just don't need to worry about other inputs.
So if you have any questions or comments, please use the chat box on the left, and please type in your questions and comments.
Okay, so there are big differences between microscopic and macroscopic models. I think I explained this one. Macroscopic models typically use average speed. So if the vehicle speed is 50 miles per hour, then it gives exactly the same result whether you have any speed variation or not. But microscopic models use like a typically use second by second speed and acceleration data. So if there's any speed variation, then it gives the impacts of the speed variation. So for example, like in signal operation project, if there's some the changes of the speed operation, then if there's no significant impacts on average speed, but it can change the movement of the vehicles, then it's gonna reduce. It may reduce the total fuel consumption emissions at certain intersection. But if you use like a macroscopic model, it doesn't give any differences. But if you use a microscopic model, then you can see the improvement of the fuel consumption emissions. Does that make sense? There's no way. Okay, the question is there a way to know the typical fleet of vehicle out there, and how many of the passenger cars and how many of the trucks and so forth? There's a default values of the in the MOVES model. So I typically use the vehicle distribution database. Also, you can get it from the, I think, some sources, but I typically use from the MOVES model default value for this the characteristic of fleet. And the next question is, can you get an aggregated impact of particular project? Yes, you can do it from the MOVES project level analysis. For example, like if you have some highway improvement project, then they're going to give you certain changes of vehicle activities. Then using that activity data, you can estimate it. You can estimate the impacts of fuel consumption and emissions using the MOVES, and or using the new method that I presented.
Any other questions? All right, so moving on to the next presentation, the attractiveness of tolling, presented by Dr. Jianhe from Virginia Tech. I'll let her start her presentation.
Okay. Thanks, Arash. Okay. Welcome everybody to today's webinar. Today I'm going to talk about the attractiveness of hot lanes. So a little bit of background information first. Toll roads in the United States started in the 18th century. The first limited access highway actually started in 1930s. It is the Merritt Parkway in Connecticut and Pennsylvania Turnpike in Pennsylvania state. So there are different types of toll roads. Originally, toll roads are used by the road builders to recover the cost of building the toll roads and allow people to buy the privilege of using that toll roads. And nowadays, most of the toll roads are used to relieve congestions on the roads. So people can pay toll roads when they are traveling along a corridor, or they need to pay a toll when they enter a congested area, such as central business district, which is usually used in Europe. And about the toll rates, you can pay a universal tolling, a fixed amount of money by just using a corridor, or there is differential tolling system, which is based on the distance or time you spend on the toll roads, or the HOT lanes, which is actually our topic today. I will come back with more details with HOT lanes later on. Method of collecting tolls, there's manual toll plaza. This is the old-fashioned way where you stop and you pay the toll and then you go. And with the development of wireless communication technologies and image processing technologies, nowadays people can collect tolls automatically. You can use the transponders, which is a detector in your vehicle, and the sensor will automatically detect your existence on the toll road, and they will charge some money. Or with the camera, it can automatically scan your plate, and you will be charged tolls afterwards. So now there are still debatings going on about using toll roads. The supporters of the toll roads believe that charging tolls to the road users will increase the revenue, and it will relieve the congestion on the roads, and also it will improve the efficiency of network. However, the opponents of the toll roads believe that it is against the social equity, and they think that actually charging a toll will slow down the traffic. No matter it is the traditional toll plazas where you have to stop and pay the toll, or even if it's an automatic payment system where the gate with the detectors will detect your vehicles automatically, you still will slow down somehow when you pass this gate with the detectors installed on them. So they also believe that the benefits of toll roads is not telling a complete story, because there's this traffic diverted from the toll roads to the free parallel roads, and that will cause additional congestion in the network, which is not incorporated when you evaluate the benefits of the toll roads. So here comes the first survey. Do you think tolling is a good solution for congestion? Oh, okay. Oh, okay. Okay, moving on. So for those of you who chose no or don't know in the survey, hopefully this picture will change your idea. At least I like this picture very much. On the right is the toll lane, and the left two lanes are two general purpose lanes. And you can see the congestion here versus the free flow traffic. Or this probably will convince you as well. This is another picture from Florida. I think this is I-95. I just screenshot this from the YouTube. The left two lanes are the HOT lanes, and the right two lanes are the general purpose lanes. Let's talk about the HOT lanes I'm going to talk about today. HOT stands for High Occupancy Vehicle / toll lanes. It's actually a relatively new idea comparing to the traditional toll roads. The first hot lane in U.S. Is starting from California, SR 91. The time was around 2001. The HOT concept is actually making use of the existing HOV lane. The whole purpose of HOT lane is to encourage carpooling, because in a HOT lane project, the HOVs can use the facility for free. You need to buy your way into the HOT lane only if you are a single occupancy vehicle driver. And usually HOT lanes, they have varying toll rates, meaning that the toll rates will update every 5 minutes or 10 minutes or 15 minutes. And it's supposed to be very efficient in improve the network. Instead of choosing a toll road or not before your trip started, you got options of buying in the way of the toll lane or not on the road. So if you take a look at the map on the right, this is 95 from Florida. And you can see the yellow arrows here are so-called accessing points, where people can use those accessing points to get in and get out of the HOT lane. That means that you have the flexibility. Instead of, you can choose a road and then just go all the way down through. However, interesting thing is that HOT lanes provide you with the flexibility, but at the same time, it gives us the complexity of modeling people's behavior when they are using such facilities. Here are several examples of existing HOT lanes in the United States. So far, there are about 15 of them. This is I-15 in California. It's a HOT2+ facility. It means that you don't have to pay if you have 2 or more people in your vehicle. The total facility is 20 miles long. The toll rate ranges from 50 cents to $8. And this is I-25 in Colorado. Total length 7 miles. It's HOT2+ as well. 2 or more people can use this for free. And the toll rate ranges from 60 cents to $5.50. I-394 in Minnesota. The total length is 12 miles. It's HOT2+. Toll rates ranges from 25 cents all the way up to $8. And I-95, this is the picture that I showed in my previous slides. The total length is 22 miles. It's a HOT3+. It means that if you have 2 people in your vehicle, you still have to pay. If you have 3 or more people in your vehicle, you can use this facility for free. The toll rates for this HOT lane is somewhere between 25 cents to $7.25. And then in Virginia, we have I-495. It's a 14 miles long facility, and it's a HOT3+. The toll rate ranges from 20 cents to $1.25 per mile. As you can see here, actually in the map, there's another blue line. It's the I-95. As far as I know, it will open to traffic actually this year, December 2014. All those examples, as we can see, that the HOT lanes are usually used in places where it is very congested. Most of these places are the metropolitan areas. And usually there's a HOV in place, but is underused. And also there's very limited space or money to expand the existing roads or build another new road. So here comes my favorite, SR 167 in Washington. This is the study corridor in my research. I think this is my favorite because this actually reminded me my work a long time ago, about like 10 years ago when I worked in a consulting company. I still remember the days when my colleagues and I were sitting in our conference room trying to raise the toll rates all the way up to $12. Still, we see a lot of congestion in our simulation results. Back then, what we were trying to do is to predict the revenues and the toll flow, the traffic flows in this corridor using the information that we know, such as the value of time in the area, traffic counts, and so on and so forth. Because there are no precedent cases back then in 2004, so we have very little experiences of studying such corridors. The HOT lane back then was really new idea. So fortunately, now all those things that we were trying to predict become historical data that I can use to study what people really react in real world to HOT lanes. SR 167 was opened to traffic in August 2008. It's a dynamic toll system updated every 5 minutes. It's a HOT 2+ facility, which means that if you are a single driver, you need to pay. And if you have 2 or more people in your vehicle, you can use that facility for free. The total length is 10 miles, and then the initial toll rates range from 50 cents to $9.50. Here's the second step survey. Which of the following factors is the most important one for you when you are driving on the road? Yeah, okay. Okay, moving on. So the operational and managing challenges for HOT lanes include the following several questions. Which toll rate you should start with? When should you update your toll rate? How will drivers respond to the toll rate? And what will be the resulting revenue and the level of services on the road? So the conventional method of answering those questions is to conduct a large-scale survey in the area. And people got to answer questions such as, what is your family income? How many vehicles are there in your household? How many vehicles are you going to use for your commute? What is the toll rate you would like to pay? Things like that. And the aggregated results will be used to generate a set of curves like this. It's a beautiful, smooth curve that everybody likes. As you can see that with the increasing of tolls, the percentage of willingness to pay, so-called the diversion rate in my project, will decrease, obviously. And the length of the project will impact on the final results as well. So you can see that the longer the project, the longer the toll length, the higher percentage of people will be willing to pay. And unfortunately, it looks like the prediction results of using such curves is not as satisfactory as people would think. And the final results of the estimation of revenues and traffic flows are not necessarily the real situation. So a lot of researchers come up with very complicated mathematical models. They're trying to include variables such as the travel time savings, the toll rates, income, speeds into the model. So here are the logit, utility model, probit models, linear models, a lot of models going on, and heuristic models where people are doing a lot of iterations to trying to find the perfect toll rates for the people. But assumptions here, I think, is that people assume everybody is reasonable. And when they are driving on the roads, they are making rational decisions. And once they make up their minds, they will not change their decisions. What I'm trying to ask here is that, is this real true? Just thinking about the situations when you are driving on the roads, what factors will affect your decisions of using a toll road or not? So I always believe that whenever there is money involved with human beings, it will not be a simple question. So let's think about all those issues, and I will come up with this conclusion that choosing the HOT or not maybe is not as simple as an engineering question or a mathematical question. It's more like a combination of engineering and a psychology problem. So let's take a step back. Instead of modeling, rushing to all those complicated factors and variables, let's take a look at the data itself. Forget about you are an engineer or you are a mathematician or statistician and you know what you're doing, you know exactly what is your time saving. Just to think about you are a regular road user. You are just driving your vehicles on the congested roads. What will you do? So let's the data talk. I requested two data sets from Washington State. The first data set is the loop detector data from UVA TTA. The data they have are very traditional data. It's by lane, the traffic counts, the year 2006, 2007, 2008, and 2010. The thing is that they know the traffic counts in each lane, but they have no idea who is paying and who is not. So I requested another set of data from SR 167 Managing Authority. What they have is the transponder data where they know the traffic counts in the HOT lane. So they know who's paying the toll and who is not. Here is a plot of the loop detector data. As we can see that, as I mentioned before, that SR 167 is a really congested corridor. It's south of Seattle. So this figure shows you the traffic volume in the northbound section 6. This is very close to the Seattle downtown. As you can see, the general purpose lane traffic volume goes all the way up to 2,500 early in the morning, around 5 or 6 o'clock. And then it stays that way until late in the afternoon, around 4 or 5 o'clock. As the dashed lines are the HOV counts, we can see that it is underused. The highest peak is somewhere around 600 vehicles. To make sure that I'm comparing apples to apples, I compared the two data sources that I get from those two agencies. The solid lines here are the transponder data, and the dashed lines here are the loop detector data. As we can see that those two data sets are very consistent with each other. There's a small discrepancy. And then I plotted the relationship between the toll rates and the percentage of SOV who's willing to pay, the diversion rate. As you can see here, that it started with a relatively level of percentage, and then it raises up, and then it stays level for a while, and it drops when the toll rate increases further. And a similar pattern for the data from year 2010. It started with a very stable percentage, and then it increases rapidly. And it stays like that for a while, and then drops a little when the toll rate is above $4.50. When you overlay those two figures together, you can see the differences between those 2 years. In the opening year, 2008, the curve actually levels out very quickly and stays like that. But in the year 2010, it's a very quick jump. And then it levels out, and you can see the percentage of people who's willing to pay almost doubled that number in 2008. Then you may have a question by now that why the diversion rate is actually increasing when the toll rate increases. So as we discussed before, the HOT lane is in a dynamic tolling system, which means that they updated the toll rates every 5 or 10 minutes, according to the traffic condition on the road. So this actually leads us to think about what is the relationship between the diversion rate versus the traffic volumes. So this figure is plotted from the data in the year 2008. It started as a slowly climbing percentage when the traffic volume is around 1,600. And then the percentage of people who's choosing to pay rapidly increases until the traffic volume reaches around 2,000, 2,200. And then after that, a level or slightly decreasing pattern shows before the road is totally congested, and then a huge drop when the traffic flow is really high. This is very understandable, because just thinking about you are willing to pay to avoid the congestion, but if it's really congested, why should you bother to pay the money but still sitting in the traffic without moving? So a lot of people would choose to get out of the HOT lane. Similar pattern here in the year of 2010. Slowly raises up and then goes all the way up, levels out and drops. And when you put those two figures together, you will be able to see the similar differences as we showed before. First of all, in 2010, people started to pay much earlier when the traffic flow rate is about 1,500. And then when it levels out, the differences is huge. 2010, about 20% of the people would like to pay, while in 2008, only 8% to 10% is willing to pay. So if you take a look at the figure here, the x-axis is the toll rates, the y-axis is the flow rate. So this is the data from 2008. As you can see that when the toll rate is low, people don't really care. When the traffic flow is only like 500 or 1,000, a lot of people choose to pay the toll and to use the HOT lane. But with the toll rates increases, this line actually retrieved a little. It pushed back until the flow rate is much higher. People would like to pay. And then a similar pattern shows here in 2010. The only difference is that people are now more tolerant. Even when the toll rate is like $2 or $2.50, people still would like to pay when the flow rate is really small, say somewhere around 500 or 1,500. It did retreat back when the toll rate raises all the way up to $3.50. So the conclusion so far is that the diversion rate, the percentage of people who's willing to pay, is not monotonically increasing or decreasing depending on one single factor. It is actually a compound effect of different variables, such as toll, flow, and speed. And the ramp-up effect, which is how people react to the project at a different stage of the project, is very obvious. You can see how people behave totally differently in the project opening year and then after 2 years when the project is in place. And this is still ongoing research. So after we let the data talk, let's move on to our regular track, let the model talk. The goal of this research is to model the diversion rate, and different variables need to be included. We are thinking about how flow rate plays a role in the diversion rate. Will it be more important than a regular road user than travel time saving? What about the density? What about the position of this driver? who's sitting in the traffic to the end of the corridor. Well, that distance makes a big difference. And I would like to do a case study, preferably for the I-95 in Virginia, who will be opening pretty soon. And I would like to see how the model will change from site to site, how it is cases dependent. Like, if the value of time varies in the area, how people will react differently. So here's the third survey. Total. It depends on the length of the highway?
Yes.
Okay. What would you like to choose?
Just choose the maximum.
Okay, moving on. What? $2. You want to choose $2? Okay. Okay, thank you very much. And I saw a lot of questions here, actually. Emily said, oh, okay. Open December 29th. Look forward to it. When you told existing facilities in alternative. Is that supposed to be a question? Andy Winch?
So the second question is
Andy Winch, could you, is this a question for me, or is just comments on the toll roads?
So I think it's a valid point. So when you toll an existing facility and its only alternative is also tolled, you have no choice but to pay the toll or get a new job or move your family. That's fair enough. This is what happened with Route 50 and I-264 tunnels
in Norfolk.
Portsmouth and Norfolk.
Yeah, right. Yeah, actually, unfortunately, it's true. If it's a tolling tunnel or bridge, there's no choice. You have to pay. But for the case that I talked about today, the HOT lanes, you do have the option of not paying anything. You can just use the general purpose lanes that run side by side with the HOT lane. Then Emily, you have a question about what do the colors signify on slides 27, 28. Well, to be honest with you, I don't think the color means anything. It's just the height of the spikes that shows you the percentages. And then Bob Joseph. Hi, by the way. The question depends a lot on what distance is covered by the toll. That's true. Yeah, I totally agree with you. Oh, okay, I see. Yeah, true. Is there any questions, comments?
Yes, there's one.
What? Which one?
Emily.
Oh, Emily. Okay. Unfortunately, Emily, I do not know the trip purposes in this case. What I can think of right now is that probably I would make assumptions of the time of the trip happened. If it's during peak hours, say if it's early in the morning, 6 o'clock to 9 o'clock, I would assume that majority of the trips are commuting trips, because this is a very important commuting corridor south of Seattle. So that is actually a very good question. I have been thinking about this. If we can incorporate the trip purposes into the data, that will contribute to the results a lot. And as for the factors, in addition to income, that would affect the use of HOT lanes, of course, there's density, there is possible time saving, because as I mentioned earlier, that as a regular road user, you may not know exactly how much time you will be saving if you're using the HOT lanes. So I would say that there are a lot of random factors playing in their roles in this diversion rate as well. So let's see what will happen after I model the data. It will be very interesting.
If you have more questions, please type in your comments. I can see someone is typing. But after the questions, please bear with us a few more minutes to answer a very short survey. Okay. Happy holidays, everyone, I guess.
Yeah.
So I guess, Jim, we are ready to start the evaluation.